Hello, welcome. Today let's try to solve another Leetcode problem. 235 lowest common ancestors of a binary search tree. So for the BST, it is a little bit easier when compared with the lowest common ancestors of a binary tree because binary search tree has a property. So if this is the root node, the value from the left side, all those values will be smaller than the root, and the right side, all those values will be greater than this root. And for the subproblem, for this 879, it also has the same property. So recursively, it has always be the same property. From the left side, it will always be smaller than the root. From the right side, the value of the node will be always bigger than this root. Yeah, we can also use the lowest common ancestors of a binary tree method to solve the problem. It is like this. Yeah, so if we are going to solve it like in a binary tree, the time complexity will be O(n). Yeah, because even it is linear or it is not linear, we have to traverse all the nodes to check. So the time complexity is O(n). Yeah, but while we are using the binary search tree, if it is a balanced tree like this, so the time complexity will be log n. So if it is not balanced, it is linear, so the time complexity will still be O(n). Yeah, but basically this will be faster than the binary tree. Yeah, because binary search tree has the property. Now let me explain a little bit about the binary tree first, because we didn't have the property of the values from the left side less than the root node, or the right side of the value is bigger than the value of the root node. We have to traverse all of them. Yeah, so I explained this solution in Leetcode 236, so I will not explain it here, just to prove this really works. Yeah. Yeah, now you can see this method also works because basically this is going to be a little bit slower. Now we're going to use the property with the binary search tree to solve the problem. Yeah. So basically we need to find the situations. If those two nodes, both of the values are less than the root node, or both of the values are bigger than the root node. And except for those two cases, we just need to, return the root. It means the root node is in between. So this is a little bit easier because there are only three conditions we need to check. Yeah, so the first condition is, and by the way, we can also check the constraints. So it is said that P and Q always exist. So it means we can always find, and the node will be at least 2 because there will be at least P and Q. Yeah, so we can use the if check directly to check the three conditions. So we're gonna check the root value. If root dot value bigger than P dot value and root dot value bigger than Q dot value. So this is the first case. So if we are going to search find 2 and 4, for example, so the root value is 6. So root value is bigger than 2 and 4. So we're gonna go to the left side, recursively go to the left side to find. So this is basically the search problem for a tree. So we can return from the left side. So self dot lowest common ancestors with root dot left, and inside it's gonna still be P and Q. So the second condition is root dot val less than P dot val and root dot val less than Q dot val. So this is the second condition. So let me copy the code. We just need to return from the right side. So for example, we are going to check 8 and 9. Yeah, this 6 is less than 8 and 9. So we're gonna go to the right side. So we're gonna return directly to the right side. So here gonna be root dot right. And finally, if it is not that case, maybe we're gonna search 2 and 8. Yeah, it is not it is not both bigger than those two numbers or smaller than both of those two numbers. So we just need to return root dot value. This is 6. Yeah, so this is easy to find according to the binary search tree property. Now let me run it to check. So the int object has no attribute val. Yeah, because I think I need to return a root. Let me check the return. Yeah, I need to return the node. It's not the value. Yeah, this is 6. I gonna need to return this node, and this is from the left side or right side. But finally, I'm gonna return the root. Let me just run it. Yeah, as you can see, it works. Now let me submit it to check if it can pass all the testing cases. Yeah, as you can see, it passed all the testing cases. And the speed is similar, but actually if it is a binary, if it is a balanced tree, yeah, it's gonna be much faster. It's gonna be log n. If it is linear, it's gonna be O(n). And also similar for the space complexity. If it is a balanced tree, so the recursive function it will be log n. So if it is linear, the space complexity will also be O(n). Thank you for watching. See you next time.